Welcome back to our deep dive. Today, we're jumping into something pretty fundamental in tech, how computers, well, how they organize information efficiently.
Yeah, making sense of all that data.
Exactly. And we're focusing on one specific method, the quicksort algorithm. It's known for being powerful, elegant even.
Definitely elegant.
Our mission today for you is to really unpack how this thing works. We want to get into its clever divide and conquer strategy.
And quicksort is such a great example of recursion, isn't it?
Recursion, right, where something calls itself.
Exactly. It takes this big, messy sorting job and breaks it down into smaller, much more manageable little sorting jobs.
Little pieces.
Little pieces. And it keeps doing that until the lists are like super small, maybe just one item.
Which is already sorted, technically.
Precisely. That's the base case.
Mhm.
And the real kind of aha moment is seeing how it puts those perfectly sorted tiny bits back together.
Okay, so conceptually, divide and conquer makes sense.
Right.
Break it down. But how does quicksort actually do it? Let's maybe take an example, like a jumbled list of numbers.
Good idea. Let's say we have 529176, just a random mix.
Okay, 529176. What's step one?
Step one is choosing what's called a pivot. You just pick one number from the list.
Any number. Or is there a strategy?
Well, how you pick the pivot can affect performance. Sometimes it's random, sometimes the middle one, maybe the median of 3. But let's just, for simplicity, say we pick 6 as our pivot from that list.
Okay, 6 is our pivot. Now what?
Now you partition. You basically go through the rest of the list and create 2 new, smaller lists. One holds everything less than 6, and the other holds everything greater than 6. That's the splitting part.
Right. So for 529176, if 6 is the pivot, the less than list would be 521.
Yep, so 521.
And the greater than list is 97.
Exactly. And the pivot, 6, just kind of hangs out in the middle for now.
Okay, so we've split it, but they're still not sorted.
Not yet. This is where the recursion kicks in. Quicksort now essentially calls itself on those 2 smaller lists. It says, okay, quicksort, now sort 521 for me.
And sort 97 as well.
And sort 97, it repeats the exact same process. Pick a pivot, partition on their smaller lists.
Wow. Okay. But, does it ever stop? How does it know when it's done splitting?
Good question. It stops when it hits that base case we mentioned.
The single item list.
Or an empty list. If a list has 0 or 1 items, it's already sorted by definition. There's nothing left to do.
Gotcha. So 521 would keep splitting, maybe pick 1 as a pivot, until you just have sorted single numbers, basically.
Exactly right. It recursively breaks down until it gets 1, 2, 5, and then it knows how to put those back together in order. 1, 2, 5.
And the same happens for the 97 list.
Yep, it'll recursively sort itself into 7, 9. This constant breaking down is why it's usually so fast, especially with lots of data. It keeps making the problem simpler.
Okay, that's the aha moment, seeing it build back up. So quicksort 5, 2, 1 gives us 1, 2, 5. And quicksort 9, 7 gives us 7, 9.
Correct.
Then what? How do we get the final sorted list?
It's actually the easiest part. You just concatenate them. You take the sorted left list, put the pivot back in the middle, and then add the sorted right list.
So 1, 2, 5. Then our pivot 6, then 7, 9.
Put it all together.
And you get 1, 2, 5, 6, 7, 9. The whole thing sorted. That's surprisingly neat.
It really is elegant, isn't it?
So let's just quickly recap the core idea. Quicksort works by choosing a pivot element, splitting the list into 2 parts based on that pivot, smaller stuff, bigger stuff.
Right.
Then it recursively sorts those smaller parts
Keep breaking it down.
until they're trivial. And then it just stitches the sorted pieces back together with the pivot in the middle.
That's the essence of it.
It feels foundational. You can see why it's used so much in databases, programming, just about everywhere you need sorting. Is there, a catch? Any downside?
Well, like most algorithms, it's not perfect in every single situation. Its performance can sometimes degrade, especially if you consistently pick bad pivots.
Right.
Like always picking the smallest or largest element in an already sorted list. That's the worst case scenario.
Okay.
But on average, for random data, it's exceptionally fast, which is why it's still so dominant.
Makes sense.
And, if we step back and think bigger picture, this whole divide and conquer strategy,
Yeah.
how could that apply to other things? Beyond just sorting numbers, think about any really complex challenge you might face.
Like a big project, maybe.
Exactly. Or even something creative. Could breaking that huge, maybe overwhelming task down into smaller, similar pieces you can tackle one by one be a useful approach?
Like mini quick sorts for life problems.
Sort of. It's that idea of making complexity manageable by breaking it down recursively. It might just be a universal key,
Yeah.
Something to think about.
Definitely food for thought. A great place to leave it for this deep dive.